Welcome everybody to today's central exercise class in Mathematics 2. We'll be discussing sheet number 10 today. As usual, there is a question, there's a chat channel for your questions, that's available on chat.tum.de. And please ask your questions on this channel here, MA9714-CE. The channel will be moderated by Eileen Carson today. And she'll either answer your questions directly or she'll forward them to me. We'll be discussing sheet number 10 today. So that's mainly on integration. We start with a problem of integration on a box. Then we have a more theoretical problem where we show that a certain function is not integrable. And finally, we have a problem 10.3 on integration about a non-box area. That can be described as a normal domain. So we'll discuss normal domains in 10.3. Okay, let's start right away with C10.1. So here we have a function, this function. And the question is, compute the volume below the surface of the graph and this rectangle here. And of course, we're going to do that by means of an integral. So the function f, once again, f of x1, x2 is given as 2x1 plus 3x2. And the rectangle D is given as the interval from 0 to 2 for x1 and the interval from 3 to 4 for x2. So that's the x1 coordinates. This is the x2 coordinates. And we're going to compute the integral over d of f of x1, x2, d x1, x2. Now, the function f is a continuous function. And for continuous functions, we know that these can be integrated over a box specifically, and we can compute the integral using iterated integration. So we first compute the integral with respect to one of those two variables, x1, x2, and then integrate the result once again with respect to the remaining variable. And as the function is continuous, Fubini's theorem holds, and Fubini's theorem basically tells us that function can be integrated and the order of integration does not matter. So we're free to choose whether we want to integrate with respect to x1 first or with respect to x2 first. The result will be the same. Also, the function f is obviously non-negative over this interval, right? Because we have non-negative numbers here. So the volume that we are looking for is exactly equal to the integral over f. We don't have to take care of any sign switches here. So let's write that down first. F is greater or equal to 0 over d, and that means the integral is equal to the desired volume. And second, f is continuous over d. That means the integral exists and we can compute it using iterated integration. And also the order does not matter. All right, so let's go ahead. Let's try to compute this integral here. Now, as I said, we are free to choose any order that we want. So for example, let's choose x2 for the outer integral. x2 goes from 3 to 4. and x1 for the inner integral. X1 goes from 0 to 2. And I usually use this type of notation here where I denote at the lower border which variable I'm referring to. Of course, that will also be apparent from the dx1, dx2 at the end, but I find it's more convenient and less error prone to also denote that with the integral sign itself. Okay, so you don't have to do that, but I suggest you do. So the function is 2x1 plus 3x2. And again, the inner integral is dx1, so that comes first. And then the result will be integrated with respect to x2. So there's dx2 at the end. Okay, so let's just compute that. We keep the outer integral. For the inner integral, it can be resolved right away. It's just an affine function with respect to x1. So if we integrate that expression with respect to x1, we get 2x1 squared over 2 plus 3x1 x2. The boundaries are 0 and 2. And then we keep the dx2 as well. Now let's substitute the boundaries. Oh, by the way, that's supposed to be an x2, of course. Sorry. Let's substitute the boundaries. So here we have 2x1 squared over 2, so that's just x1 squared. Upper bound is 2. So we get 2 squared plus 3 times x1 times x2. So that is 6 x2 minus the lower bound. The lower bound is 0. So we get minus 0 here and minus 0 here. And that's again an integral in just one variable, x2 this time. And we need to compute. And that's also easy to do. So here we have 4 plus 6x2. To integrate that, we obtain 4 x2 plus 6 x2 squared over 2. And the bounds are 3 and 4. So what we get is 4x2 upper bound is 4, so that's 4 times 4 plus 6 over 2 is 3, so that's 3x2 squared. So we have 3 times 4 squared. Minus the lower bound is 3, so we have minus 4 times 3. Minus 3 times x2 squared, so that's 3 squared. So what do we get here? 4 times 4 is 16, plus 3 times 16 is 48. Minus 4 times 3 is 12, minus 3 to the power of 3 is 27. So in total, that is, let's see, 16, 452, 25, if I'm not mistaken. So that should be the volume that we're looking for. Okay, any questions on this problem?
Nope, nothing so far.
Nothing so far, wonderful. Then let's go on right away. C10-2. So in C10-2, we have a function, this function here, defined on the open interval from 0 to 1. And the task here is to show that this function cannot be integrated over that domain here. Okay, so the function f x1, x2 is defined as x1 minus x2 over x1 plus x2 to the third. And I already mentioned Fubini's theorem. Now, Fubini's theorem holds for all integrable functions. So we know that for a function that is integrable, we can compute the iterated integrals in any order, and the result will always be the integral. In particular, no matter what order we choose, the result will always be the same. And that's what we are going to use here. So if the function was integrable over D, then by Fubini's theorem, the order of integration doesn't matter. So we just compute the two integrals, reversing the order. And if you find that the result is different, then that means the function cannot be integrable over D, over that domain. And that's exactly what we prove now. So if f was integrable, by Fubini's theorem, we would have that the integral from x1, equals 0 to 1, and inner integral x2, 0 to 1. So that integral here, dx2, dx1, that would be equal to the iterated integral in the other order. So if the outer integral is the x2 integral, and the inner integral is the x1 integral, f of x1, x2, dx1, dx2. And we will show that this is not true here. So that's the basic idea in that problem here. And of course, integrating that function is not as easy as the other one was, but it can be done. So let's try to do that. We'll start with x1 as the inner integral. So we first compute the integral for x2 from 0 to 1 over the integral for x1 from 0 to 1 of the function f, and the function f is, remember that is here, x1 minus x2 over x1 plus x2 to the power of 3. So we can write that as x1 minus x2 times x1 plus x2 to the power of minus 3 dx1 dx2. And then for computing this integral, what we can do, for example, is we can use integration by parts. So we could use this here as a function f, and this here as a function g prime. And then using this substitute, or this integration by parts rule, we get rid of that f. Yeah, because we'll use the derivative of f further on. And of course, that means we completely get rid of that expression. So that's the idea. We do integration by parts for the inner integral, right? With this here being f of x1, and this here being g. G prime. Okay, now let's see what we obtain this way. The outer integral stays in place. For the inner integral, if we do integration by parts, the first thing we get is f times g. So that means this f here is kept intact, x1 minus x2 times, and then we have to integrate g prime. Now the integral of an expression, something to the minus 3, you know how to integrate that. That is something to the minus 2 divided by minus 2. right? The reverse of differentiation. So we get this here, x1 plus x2 to the -2, and we have to divide by -2. So we multiply by -1/2. Let's write that in front here. Okay, we have to evaluate that in the boundaries, x1 from 0 to 1. And then, then we subtract the integral of f prime times g. We have computed g already. Remember, that's this expression here times -1/2. So instead of minus the integral, we get +1/2. The integral of x1 plus x2 to the power of -2 dx1. And f prime, well, if we differentiate this expression with respect to x1, we just get 1, right? So that part vanishes. That was the whole idea. And here we have x1 from 0 to 1, of course. Okay, so that's the inner integral. And once we have computed that successfully, we still have to integrate with respect to x2. So let's go about integrating this one. Outer integral stays. Now for the inner integral, let's see. We get for the upper bound, we get 1 minus x2 here, 1 plus x2 here. So all in all, we have minus 1 minus x2 over 2, and that's 1 plus x2 squared. That's the upper bound. For the lower bound, 0, we get minus 1/2, so that's a plus again. And here we get minus x2 times x2, minus x2 over, over x2 squared. And I forgot 2x2 squared, yeah. So that's this first part here. And then, of course, we have to compute this integral. And that works in the same way as we already tried before. So we have something to the power of -2. We integrate that. That yields something to the power of -1 divided by -1. So what we get is plus 1/2. And then we have 1 over x1 plus x2. And we have to divide that by -1. So we just take out that minus and write it here. And again, boundaries x1 from 0 to 1. And let's close the outer integral. Okay, so we're almost done with the inner integral. Again, let's copy that outer integral sign here. Let's see what we can do to simplify this a little, possibly. So first, this first expression here, we can take in the minus. That's x2 minus x1 over 2, 1 plus x2 squared. Then here we can cancel out 1x2. So that's minus 1 over x2. Minus 1 over 2x2. And then here we get, let's see, upper bound is 1. So we get minus 1 over 2, 1 plus x2. And the lower bound is 0. So we get plus 1 over 2x2 dx2. And finally, there's no x1 left. So again, let's see if we can simplify this a little more before we start integrating. So what do we have here? We have this expression minus 1 over 2x2 plus 1 over 2x2. So those two cancel out. Until we have 2 over 1 plus x2 squared and 2 over 1 plus x2 without the squared. So maybe we can rewrite that a little, get it all into one expression. So what would that mean? We would have x2 minus 1 here. And then instead of the minus 1, we get minus 1 plus x2 over 2, 1 plus x2 squared, right? dx2. And that means here we have an x2, here we get minus x2, so those cancel out. And here we have a minus 1 and another minus 1, so that's a minus 2. And that cancels out with that plus 2 here. So we're left with a minus sign in the numerator, and the denominator stays the same. So simplified version of that integrand is that is minus 1 over 1 plus, 1 plus x2 squared dx2. And again, that's basically 1 over 1 plus x2 to the power of minus 2. So using the usual integration rule for polynomials, we can integrate that. And we get 1 over 1 plus x2 divided by minus 1. And then we have this minus 1 here, so those cancel out. So that's what we get for the integral, and we still have the two boundaries here. And now if we substitute those, we get for the upper bound, we get 1 over 2, and for the lower bound, we get 1 over 1. And that yields a total of minus 1 over 2. Okay, so that took us some time, but conceptually not too hard to do, I hope. Any questions so far?
Nope, still nothing. So I guess conceptually not that hard.
Okay, wonderful. Or if you want, fell to already. Okay, so we have computed the integral with x2 being the outer integral, x1 being the inner integral. Let's try the other way around. So now we need to compute the integral with x1 being the outer integral, x2 being the inner integral of x1 minus x2 over x1 plus x2 to the power of 3 dx2 dx1. And as you might imagine, we can, of course, just repeat the whole procedure to get the result, basically use the same techniques, or we could use a little trick. And as I've shown you the whole procedure already, I'm going to show you that trick now. But that really only works because we have done the work at least once. What we're going to do now is we're going to use the fact that that function is basically symmetric, right? So here, the order of x1 and x2 doesn't matter at all. Here it does. There's this minus sign in here. But what we can, of course, do is we can factor out that minus sign. So we can say this is minus the integral from x1 over x2 of x2 minus x1, x2 plus x1 to the power of 3, dx2 dx1. And now basically that's the same function as before, but the order of x1 and x2 has changed. Formally, what we could do now is we could make a simple substitution. So we could say, well, let's substitute, introduce new variables. Let's call them C1. C1 will be the same as x2, and C2 will be the same as x1. So those do that swap of the two variable names, actually. right? Then of course, dc1 by dx2 is 1, dc2 by dx1 is also 1. So that substitution doesn't do a lot. But what it does do is it changes the naming basically, yeah? So instead of x1, we would now write c2. And if we substitute the boundaries 0 and 1, of course, c2 has the same boundaries as x1 has. So that's 0, 1. Then the inner integral becomes c1 from 0 to 1. And the function expression becomes c1 minus c2 over c1 plus c2 to the power of 3. And we integrate dc1, dc2. And as you can hopefully see, that is the very same integral that we have just computed. Only difference is instead of x, we now use c for the variables, but the name doesn't really matter for the result here. So of course, the result will be the very same. So what we get is, this is minus, and then this integral here, we've computed that before. The value of that, you'll remember, was minus 1 over 2. So we get that from above. And that means that integral has a value of plus 1 over 2. So obviously, that's not the same as before. The two values that we get are different, and that means the function cannot be integrable. So the values are different. Depending on the order of integration. And that means f is not integrable over d. Okay, that concludes 10.2. Questions?
Yes, I finally have one. So isn't the negative result for an integral already a sign of f not being integrable over the given domain?
So by a negative result, you mean a negative number? The answer in that case would be no, that's not a sign of anything useful. I mean, compare that to one-dimensional integration, right? If you have something like a function that looks like this in 1D, of course, if we compute the integral, say from here to here, yeah, that would be basically this area, but with a negative sign because it's below the x-axis. And that doesn't mean the function is not integrable. And of course, the same can happen in higher dimensions as well. Yeah, so you have your domain, and you may have the surface of the function above or below that domain. And depending on where that is, the sign might change without any other consequences. That's the only question.
So now there's another one as well. Could you maybe outline why functions would not be integrable over a certain domain?
There may be lots and lots of reasons for that. So it doesn't...
But in the case you have here, you could pinpoint a little bit, right?
In the case I have here, so basically the problem is that we have this denominator here, this part here, x1 plus x2 over 3, and the domain, remember that was domain was 0, 1 squared. So you can see what happens here. If x1 and x2 get closer to that point 0, 0, then of course this domain, this denominator gets closer to 0, and also the numerator gets closer to 0. But we have a power 3 here. So basically what happens is the denominator goes to 0 faster than the numerator. And that means the function value will tend to infinity or minus infinity, depending on the signs. And well, basically what that means is there may not be an integral value for that. There may be situations where this will work. In this case, it doesn't.
Okay. And then there's one question. Is there generally a rule for which variable you should integrate over first? As it gets very complex if you start with the wrong one.
Yeah, that may be the case, but no, unfortunately, there's no general rule for this.
That's why you need practice.
Yes.
Practice makes you a lot better at guessing which one will make it easier.
That's right. And you're right. If you guess wrongly and try the wrong variable first, you might end up with a very complicated and time-consuming integration if things go badly.
But if
I think there was an example in the lecture that shows that order of integration does matter in terms of complexity of computation, but not in terms of the result if you have an integrable function. Yeah, it's only practice basically that helps you.
So I think that's as many questions as I see about this problem.
Good. So let's go on with the last one then. 10.3. So here we have an integral over a non-box. First problem, we don't have a box. We have a triangle with given vertices, and we want to integrate that function here. So that triangle with what we call a normal domain. Let's first make a quick sketch to see what that does. So, so positive. So let's see something like that here. X1. This is going to be x2. The points are 0, 0. That's of course here. 0, 0. Then we have 3, 0. Let's see. 1, 2, 3. 1, 2. So 3, 0 is here. And then we have 0, 2, which is roughly here. So that means the triangle that we want to integrate over is this triangle here. Okay, so that's our triangle, that's our domain B. And now if you want to integrate over such a non-box domain, we have to come up with a description of that domain first that helps us doing the integration. And what often helps is trying to describe that domain as a normal domain. That's what we're going to do here. Basically, what that means is that there is an order of integration where you can evaluate all the integrals one after the other if you just stick to that order. And in each step, eliminate one of the variables. So what we need for that is one variable that is just bounded by constants. And that's going to be the outermost integral. So once we're down to that one variable, we can evaluate or compute and evaluate the integral because everything else is constant. Then the next variable is bounded by functions, upper and lower bound functions, that may depend on that first variable. The next stage will then be bounds that may depend on the first two variables, and so on. And what we do then is we basically put the expression with the most dependencies as the innermost integral. We integrate that first. We get rid of that variable that way because it doesn't appear in the bounds itself. And then we repeat that process, getting rid of more and more variables until we get to the one that's bounded by constants. So how does that work in this case? Maybe it's best to look at that by means of an example. So what can we do to describe this as a normal domain? For example, we could say, if we look at x1, then the range of x1 is bounded below by x1 equals 0. So this being a lower bound would of course mean x1 is greater or equal to 0. And the highest x1 value that we get is this one here. So x1 is less or equal to 3. Now if we have that, we can then try to bound x2 in terms of x1. Now, the lower bound of x2, this one here, is simply constant. x1 is greater or equal to 0, even better. And then we have that upper bound. And as the upper bound, we now need to use this line here, right? We can't use that line because then we would use the whole, well, we'd have the whole box. Now this upper bound of x2, that must depend on x1. So depending on the value of x1, for example, here, we'd have to get an upper bound of this for x2. Here we need that upper bound. Here the upper bound is 0. Here it's 2, and so on. So basically, we want the description of that upper bound is a function of x1. And of course, that means we need an equation that describes this line here. And that's easy to get. So the equation for that line would be, well, x2 can be described as 2 minus, and then let's see, what's the slope of this line here? Well, here's a difference in x of 3 and a difference in y of 2. So the slope of that line is 2 over 3. Right? So it means the points on this line can be described by the equation x2 equals 2 minus 2 over 3x1. And that means if we use that as the upper bound, that turns into the inequality x2 is less or equal to 2 minus 2 over 3x1. So basically x2 for a given value of x1 varies between 0 and that line, like here, or here, or here, or here. And x1 varies between 0 and 3. And that way we can finally compute the integral. Oops. Now we want to integrate f of x1, x2, dx1, x2 over that domain B. And we can write B as all x1, x2 in R2 with the property. Well, for x1, we get 0 is less or equal to x1 is less or equal to 3. And for x2, we get 0 is less or equal to x2 is less or equal to 2 minus 2/3 x1. So this bound here depends on x1, and that means this integral over x2 has to be the inner integral, innermost integral. And if we get rid of x2, evaluating that integral, we still will have x1 because it enters in the bound. Yeah, and of course, it may also remain in the function. And then in the outermost integral, we'll integrate with respect to x1, get rid of that. Okay, so what we have to do is we'll have to use the outer integral as the integral over x1, 0 to 3. And then the inner integral over x2 from 0 to 2 minus 2/3 x1. So the bound depends on x1, as you can see. And the function was x1 times x2 squared dx2 dx1. So let's compute that integral here. Just copy this outer integral first. Evaluate the inner integral. If we integrate that here with respect to x2, then we get x1 times x2 to the power of 3 over 3. So the result here is x1 times, times x2 to the power of 3 over 3. For x2 from 0 to 2 minus 2/3 x1. And the result will be integrated dx1. Now we just have to do the computations. Again, let's keep the outer integral in place here. Now that inner integral, if we substitute for x2, this expression here, we get x1 times 1/3 times 2 minus 2/3 x1 to the power of 3. And for the lower bound, let's see, we get minus x1 times 0, so minus 0. And we need to integrate that dx1. Okay, so we just need to do the computations here. Before we evaluate the actual integral, let's try to simplify this a little, possibly. So that's the integral from 0 to 3. And what we get here would be, let's see, 1/3 x1, and this is going to be 2 to the power of 3 minus 3 times 2 squared times 2/3 x1 plus 3 times 2 times 2 squared over 3 squared x1 squared minus 2 to the power of 3 over 3 to the power of 3 x1 to the power of 3. Generalized binomial formula. dx1. All right, so what we get is, let's see, oops. Again, this integral here from 0 to 3. If we multiply that x1, take that into this expression here, simplify that a little, still complex enough, but oh, what the heck. So what we get is 2 to the power of 3, that's 8. 8 over 3 x1 minus, here we have 3 that cancels out, so we have a minus 2 to the power of 3, that's 8 minus 8 over 3 x1, that's nice. At least we get rid of that one. Then actually, I think I forgot something. Yeah, I forgot an x1, right? So of course that should be x1 squared. Yeah, sorry. So we don't get rid of anything. This one here, 3 that cancels out. So we have again 2 to the power of 3. So that's 8 over 9 x1 to the power of 3. So plus 8 over 9 x1 to the power of 3. And finally, no 3 to cancel out here. So we have 8 over 9 times 9, 3 to the power of 4. So minus 8 over 81 x1 to the power of 4 dx1. All right, I hope I didn't mess up anywhere. So let's do the integration, final step, almost final step. So 8 over 3 x1 integrated, that's 8 over 3, oops, 8 over 3 x1 squared over 2 minus 8 over 3 x1 to the power of 3 over 3 plus 8 over 9 x1 to the power of 4 over 4 minus 8 over 81 x1 to the power of 5 over 5 and the boundaries are 0 to 3. And now we just have to do the computations. So let's see. That's 8 over 3. The 2 can cancel out here. So we have 4 over 3 times upper bound is 3. So that's 3 squared is 9. Minus 8 over 9 times 3 to the power of 3 plus 8 over 9. You can cancel out the 4 actually. So let's do that. That's 2 over 9 times 3 to the power of 4. And here we have 8 over, so that 81 was 3 to the power of 4 times 3 to the power of 5 over 5 minus, and the lower bounds are all 0. So let's see, 3 times 9 is 3, that's 12 then here. 9 is 3 squared, so that leaves us with minus 8 times 3. Then we get plus 2 times 9 minus 8 over 5 times 3. And let's see if I did the computations correctly. Seems good. That should be 6 over 5 in the end. And that's the result that we get here. Yeah. So basically, the take-home message here is for an integration domain like this, you will usually use a normal domain. And that means you first have to identify the right order of the variables. And just by the way, as a side note, of course, we could have done this differently here as well. We could also have said x2 is bounded by 0 and 2. And then the x1 bound would be this one and this one. So we could have basically solved this here for x1 and then reverse the order of integration with a different bound. That's not always possible. Depending on the domain that you have, the order of variables might be fixed. In some cases, there might be different possibilities, but one might be easier than the other. And again, there's no general recipe for seeing that. You just have to need to have some experience for that. And in some cases, you have 2 possibilities, and it doesn't really matter what you choose. That would be such a case here. So if you want to give it a try to compute this with reversed order and suitably adapted description of that normal domain here. Okay, questions?
Yes, so I have a couple. In the lecture, there was an example where the original function was replaced by just a 1. When exactly are we doing this? It's not 100%.
So I guess if I remember correctly, you're probably referring to volume computation or integrability. I'm not quite sure. So what we did is we defined the volume of a certain domain by saying the volume is defined as the integral of the constant function 1 over this domain. Yeah, so basically we take the domain, we put a cylinder on top of that domain up to the level 1, and then we say, well, the volume of this is the integral over the function 1 over this domain. And that's what we did here. So that's the definition of the domain, of the volume of a certain set.
Okay, and then there was one question. In theory, we are computing a volume in 10.3, right? Question mark.
Yes, basically, yes. We are computing the volume of the surface of that function, x1 times x2 squared, over that triangle. That's correct.
Yeah, and if someone is having a hard time visualizing it, I found a picture that I posted in the answer.
Okay, great. So have a look at the chat. You can see that picture.
And then, okay, let me just see. This answer helps me out. So there were a couple of like unrelated questions, but more about the course. So I don't see any more about the exercises, so maybe I should do those. So one was if there will be another Q&A session round.
Yes, we're planning on another Q&A session round. We'll be discussing details this Thursday in the team meeting, hopefully. So the idea was to offer more Q&A sessions towards the end of the semester, basically for exam preparation. We found that interest in the Q&As was getting very low. So we had about 2 or 3 people participate per Q&A. So we decided to put that on hold and then offer more Q&As during the last 1 or 2 weeks. So you can all get rid of your exam-related questions, hopefully.
And then there was one question about how many lectures are remaining in the course, roughly.
I'm not quite sure about the exact number yet. So we'll have currently 76 videos, and maybe there'll be one more, or maybe I'll split one into 2. So 76, 77, something like that. That's the number of videos that we'll have. So if all it goes according to plan, we'll be able to stop with doing new stuff a little early. So maybe we'll have the last week lecture free, so that you can spend more time preparing for the exam and ask any questions that you might have. Yes. And by the way, referring to Q&As, the lecture Q&A, of course, will still take place on a regular basis. I had to cancel that on short notice last week. Sorry for unrelated circumstances, but we will have a lecture Q&A this week.
And then the follow-up on how many lectures are remaining, how many of them will be relevant for the exam?
All of them will be relevant for the exam, as usual.
Okay, and then there's one last question about the exercises. So one integral and a function means a surface, or 2 integrals and 1 as the integrand.
I'm sorry, I didn't get that question.
So I think if you're integrating over a function, if you have some function in one variable and you're integrating over that, it should give you a surface. That sounds correct to me in some sense.
If you integrate a function, so it gives you if you integrate a one-dimensional function, basically, yeah, it gives you an area. Yeah, okay.
So a surface, something 2-dimensional. Yeah. And then if you have 2 integrals, so integral over 2 variables, but the integrand is 1, so your function is 1, that's also a surface or an area. That sounds still correct.
So yeah, basically it's now volume, right? So if you have a function that depends on 2 variables, that function defines a surface, and the integral over that, over some domain, will be the volume on top of that domain, basically, right? So a 3-dimensional volume now, instead of a 2-dimensional volume before. And of course, you can take that to higher dimensions.
And then, and then we have for a volume 2 integrals and a function. But then it's the same misconception. It's either 2 integrals and a function, or 3 integrals and a 1 as the integrand. Should give you a volume as the question, but it should be a function of 2 variables gives you a volume, but if you have like a triple integral over 1, it should give you something 4-dimensional.
Yeah, so then the domain would be 3-dimensional, right? So you have a 4-dimensional volume. Yes. Yeah.
I'll also type out the answer to that.
And of course, that volume might not be quite what we expect depending on the signs of the integrants, right? So you might have to use absolute values if you really want the volume.
And then there's another question. Are they going to get a rehearsal exam?
Currently, things are looking good. So currently you get the right pass rates for the exams, barely, but you still pass. The participation is a little hard to assess, actually. So problem is, I think I announced that we needed 50% of 50% participation rate in the quizzes. And I have a hard time determining what the base here is. So how many active participants do we still have overall? Depending on which estimate I use here, you're still barely within that 50%. So if you keep up that good work at least the same rate, preferably a little more, then you should be able to get the rehearsal exam.
And maybe you can also finally comment on the quizzes being open.
On the quizzes being so, Julius, the quizmaster has created one quiz called the Big Quiz that includes all the questions from the former quizzes. So instead of reopening those old quizzes, the new questions just go into that big quiz after they are closed. So you can just take that, and there's all your questions in the big quiz. Yeah, and keep checking back. That will continue to extend throughout the semester.
Okay, that's as much as I see. I don't see any other questions.
Okay, wonderful. So we're done on time, even a little ahead of time. So that means there's still 4 minutes to get some ice cream. So thanks for participating. As usual, I hopefully see you on Thursday in the tutorials. If you have any questions, you're welcome to ask those questions there. And otherwise, I hope I'll see you next Monday in the next central exercise session. Also, as usual, thanks a lot to Island for moderating our chat. Goodbye.